Okay, good evening. It's Sunday at 8 p.m. on October 8th, and this is my module demonstration. Before I begin, I just want to emphasize that this is a perfectly imperfect module, and I decided to demo the slides from RStudio so that you can see that you can produce slides or slide presentation using R code through RStudio. I have multiple screens. One of my screens, I'm not going to display them, but one of them has a countdown timer, and I will start and stop it just like all the other modules. I have 15 minutes. I shouldn't take 15 minutes. Remember, I'm not introducing any of the articles. My aim here is to just provide the raw materials that are necessary for you to understand a perfectly imperfect demonstration of the module 2. Okay, so well, I guess without further ado, it's 8:09. I'm going to begin right now. Okay, so this is material that is pertinent to both scale development as well as hypothesis testing. And I'm going to begin with just a little data summary because this is useful for me to understand what I'm using in order to understand the scale, the potential scale, and the data that I have so that I can demonstrate that what I do have, I can analyze. So you can see here, I start with 10 variables, x1 to x10. I'm going to assume that those 10 variables all come together to form a scale. I have an n of 30, and it looks like I have varied means, but some are negative. Standard deviation, they all look like they have about a standard deviation of about 0.8, maybe a little higher. And the standard error, the means, are roughly the same between 0.14 and 0.17, but those are all the same to me. So that's a data set that we have. I'll get back to sex and Y1 and Y2 later. To begin, this is our scale development material relates to classical test theory, and classical test theory is pretty straightforward. There's a lot of assumptions underlying classical test theory, but it's also recognized as true score theory, and classical test theory assumes that observed score variance equals true score variance plus error variance. And the reason why that's relevant is so that we can understand that variability that we observe in our scores and our total scores are a function of some underlying true score variability as well as error, and that that measurement contains error or is error prone. And then to assess reliability, it's a good way to have a central theme of understanding reliability. And reliability, as Fred Lord says, is a ratio of variances. It's true score variance over observed score variance. So as error increases, the denominator increases, and therefore the quotient decreases. Therefore, reliability, or any estimate of reliability, is going to be a function of largely the error variance. And for this module and this demonstration, I'm going to use Chromebox Alpha as the test for estimating rho. So I have a classical test theory analysis, and you'll see here R just will spit out using the PSYC package and the alpha, and specifically the alpha function will tell me if certain items were negatively correlated with the total score. Those are item total correlations, and in this case I asked it to rescale them. So you'll see here items 2, 5, and 8 were rescored because they were negatively related. And it looks like the overall alpha of this is going to be somewhere around 0.92. I do have a specific estimate of it, but these are all alpha values if those items were deleted. With only 10 items, you know that for every single one we delete, it will adversely affect Chromebox Alpha, because Chromebox Alpha is very sensitive to sample size. Sample size not in the sense that it's the number of observations, but it's the number of items. Very important. So, so not only do I have classical test theory results in that way, but here are the alpha changes that I just displayed, and these are the raw alpha, and what happens if I change the scale by dropping an item. And you'll see here that for one of the items, it doesn't really change. Or thereabouts. This red line indicates the overall alpha for the entire scale. So next is I want to show a hypothesis test, and here I've got an F test, and the F test is, or it's an ANOVA, but it's just like a T test, and the F test is comparing sexes, males, females, on Y1. And you'll see here that there's a significant effect, which means that males and females differ on Y1 significantly, certainly below the 0.5 level. And remember, there's lots of asterisks there. It's a teeny tiny p-value, so therefore the data, it appears to be the data that are not or inconsistent with the null, and so therefore we reject the null. Next is the computation of the effect size. The effect size is just the difference between the two means, and the means for Y1 and just Y1 for males and Y1 for females, divided by the pooled standard deviation. That is the variances. It's the average variances for Y1 for males and for females, and then the square root of that. So that's Cohen's d, and this is Cohen's d. It's 2.62. And the reason why that's relevant is if I have a Cohen's d, a large effect size, I can calculate power. So I have two levels, and I have an n of 15 because I had 30 people in total, and 15 is in each group. And with a large effect size of 2.62 and a significant level of 0.5, my power is 1. So I had a probability of rejecting the null that was almost certain with such a large effect size. And that's the nature of this module. So this is my demonstration, and I want everybody to watch it and to think about things that I didn't cover or that I should have covered, and post them on the form as I've posted the form link to everybody. That took me 6 minutes and 35 seconds. Thank you very much, and I look forward to reading your questions and then answering them later.